In this video, I'm going to be working some polar free response questions from previous Cal BC exams. All right, first one I've got is 2014 BC number 2. And it comes with a figure, and that's my best rendition of it. And it says, let R be the shaded region that's inside the graph of R equals 3. Okay, so that's going to be R equals 3, this semicircle. And wait, out there. What did I say? Inside the graph of R equals 3 minus 2 sine of 2 theta. So that would be this kind of lumpy looking curve. All right, so what we're going to need to do is we're going to need to integrate on the blue one, which, yeah, there we are. We're going to need to integrate on the blue one up to pi over 2, and then on the red one up to pi. Now, the red one up to pi, you could probably use a geometry formula for that, but I'm not going to. I'm just going to say, all right, A is find the area of R. Okay, well, that's going to be 1/2 R squared d theta. Okay, so the first one is the blue one, so 3 minus 2 sine 2 theta. It's R squared d theta. And we're going to go from 0 to pi over 2. Then I'm going to add 1/2 R squared d theta from pi over 2 to pi. And in this case, this R is 3. And honestly, this is the type of thing that you're going to put into a calculator anyway, and I trust y'all on that, so in the interest of time, I'm going to just move on to part B. Okay, find the value of dx d theta at theta equals pi over 6 for the curve r equals 3 minus 2 sine 2 theta. All right, so they want us to find dx d theta on the blue curve at theta equals pi over 6, and we can do that. So we need to first have x as a function of theta. And remember that x is r cosine theta. And r is 3 minus 2 sine 2 theta. And yeah, if you're going to have to use the product rule anyway, you might as well just say 3 minus 2 sine 2 theta multiplied by cosine theta. All right, dx d theta. I'm going to take the derivative of that expression, so I'll take the derivative of the one on the left first, so that'll be negative 4 sine. No, negative 4 cosine of 2 theta. Multiplied by cosine theta. Plus, leave this thing the same, 3 minus 2 sine 2 theta, and multiply by the derivative of cosine, which is negative sine. All right, dx d theta at pi over 6 would be negative 4 times the cosine of pi over 3 times the cosine of pi over 6 plus 3 minus 2 times the sine of pi over 3 times negative sine of pi over 6. And that is an ugly number, but it is your answer. Okay, that's a safe place to stop. You could also have done this using Math 8 on your calculator, because this is a calculator active problem. That is an option. Okay. But you can also do it by hand. It's not that hard. The distance between the two curves changes for 0 to pi over 2. It's true. Find the rate at which the distance between the two curves is changing with respect to theta when theta equals pi over 3. All right, distance between the two curves. That's basically this, right? When theta is pi over 3. So this distance, I don't know, I'll call that n, which changes with respect to theta, is equal to just the difference in the two r's. That's 3 minus 2 sine 2 theta which conveniently is just 2 sine 2 theta. Wonderful. Okay, that's the distance. Find the rate at which the distance between the two curves is changing with respect to theta when theta is pi over 3. So that's basically, they're looking for the derivative of distance with respect to theta at theta is pi divided by 3. Well, that'll be 4 cosine of 2 times pi over 3. All right, well, we need to think back to pre-calculus, and cosine of 2 pi over 3, not very far to the left, that's negative 1/2. And that's negative 2 units per radian, I suppose. That is a nice number, isn't it? I thought so too. All right. Oh, and then part D. Okay, I like this. I'm glad we're getting one of these examples in here. All right, part D is, now I've been seeing this type of question quite a bit, where they're going to say a particle is moving along this polar curve, and it's kind of a related rate question. So they're saying d theta dt is 3, looking for dr dt at theta is pi over 6. Okay, and this is along the blue curve. So taking the derivative of the blue curve with respect to t, dr dt is, you take the derivative of negative 2 sine 2 theta, negative 2 sine of, wait, that would be, yeah, minus 4 cosine 2 theta times what? The derivative of the inside. Yeah, d theta dt. Right, they said that d theta dt is always 3. So at pi over 6, that's negative 4 cosine of pi over 3 times d theta dt. And that's how you do it. You just have to remember, because of the chain rule, this business right here. Okay, otherwise you'd be like, what do I do with this d theta dt equals 3? How do I get this? All right, the next one I've got for you is from 2013. It was the second one. It was just another pretty old-fashioned polar problem. It says the graphs of the polar curves r equals 3 and r equals 4 minus 2 sine theta are shown in the figure above. The curves intersect when theta is pi over 6 and when theta is 5 pi over 6. And, well, part A is let S be the shaded region that's inside the graph of r equals 3 and also inside the graph of r equals 4 minus 2 sine theta. Find the area of S. All right, so there's a bunch of ways we could do this. I think what I'm going to do is I'm going to kind of just, just going to do it starting at 0 and going all the way around to 2 pi. There is definitely a more efficient way to do this, but I think that, your first inclination is probably going to be the best option for you. And for me, the first thing I thought to do is just start with 0, integrate along the red curve up to pi over 6, then integrate on the blue curve from pi over 6 to 5 pi over 6, and then go from 5 pi over 6 to 2 pi back on red. So what I'm going to do is I'm going to say the area is going to be 1/2, start going 0 to pi over 6. R squared would be, the red one squared is 9 d theta plus, oh, forgot the half. Okay, I'll go from pi over 6 to 5 pi over 6. And then 1/2 r squared would be 4 minus 2 sine theta squared. And so now, okay, I started at 0, I went over and got that much area, now I've gone all the way over to here, and so now I need to swing back along the red, all the way from 5 pi over 6 to 2 pi. and that would be the red one squared would be 9 d theta. And that is the type of integral that you can type into a calculator and get a reasonable number back for. But I'm not going to waste any time on this video by pulling up a calculator and showing you how to type in that integral. You already know how to do that. In part B, they say that a particle moves along the polar curve. Again, more motion along a polar curve. So this particle moves along the polar curve so that at time t seconds, theta is t squared. Find the time t between 1 and 2 for which the x-coordinate of the particle's position is -1. All right, well, it's moving along the blue curve. So x along the blue curve is going to be equal to r cosine theta. Well, r is 4 minus 2 sine theta multiplied by cosine theta. Now they're saying that for this particular particle, theta is t squared. So that means that x of t is 4 minus 2 sine theta is t squared cosine of theta, which is t squared. Right, well, we want to know where this is equal to -1. So I'll just say x of t equals -1 when t equals, okay, I highly doubt that we're going to be able to figure out a time by hand that that's going to work. What we're going to do is we're going to bring in the calculator. Okay, so I brought in the calculator. I've gone over here, I've plugged in this for y1, but if I'm interested in where it's equal to -1, sometimes it's smarter to add over the -1 and find where this is going to be equal to 0. Okay? So since they said that we want to make sure that t is between 1 and 2, I'm going to just say that that x minimum is 1 and that x maximum is 2. Not sure if this is a wise choice, but I'm just going to cut the scale down in y as well. So I'm going to grab, there it is. Okay, that's going to be the time I'm interested in. So I'm going to calculate the 0, go to the left of it, go to the right of it, give it a guess. And you get 1.428. And for part C, it says, find me the position vector in terms of t, and find me the velocity vector at time t equals 1.5. Okay, well, the position vector will be, we already know how to do that from our study of parametric equations, x of t and y of t. Okay, we know that x of theta is r cosine theta, which we just wrote down earlier, and I probably would have been smart to copy onto the clipboard or something, but that's okay. And then y of theta is r of theta times sine theta. Okay, so this is going to be, okay, so x in terms of theta is r cosine theta, like we said before. 4 minus 2 sine theta, but cosine theta. R sine theta would be 4 minus 2 sine theta times sine theta. But they wanted at time t, in terms of t. So what I'm going to do is I'm going to go use that identity, and wherever I see theta, I'm going to replace it with t squared. Okay, is that easy? That's the first part. And then the second part is find the velocity vector at time t equals 1.5. Now the tricky thing here is we're going to need to tell the reader what we're doing here. Okay? we're taking the derivative of each of these components at time t equals 1.5. So what I'm going to do is I'm going to first write, a little bit to tell them what I'm up to, what I'm thinking. So v of 1.5, the velocity vector at time t equals 1.5, is going to be equal to x prime of 1.5 comma y prime of 1.5. And so I might go ahead and plug this in. 4 minus 2 times the sine of 1.5 times 1.5 is 2 1/4 times cosine of 2 1/4. Nope, no, I'm doing the wrong thing. I'm just plugging in directly on the position vector. Okay, this is not what I wanted. Excuse that. Okay, I'm not going to just go in and change video, but I am going to bring in a calculator to use Math 9 for this, because you do not want to use the product rule, chain rule, all sorts of rules for that, and that's not what you want. All right, so I brought the calculator back up, and it was still on the y equals screen, and I'd had all this work from when I'd done the earlier part of the question. I'd solved for when is x equal to -1. So what you want to do is, I would just recommend making y1 given, to be just this 4 minus 2 sine of t squared. Okay, I like that, because then when I go to use Math 8 to find these derivatives, I'm just going to call on y1. So I'm going to first find x prime of 1.5. So x is r of t, which I stored into y1, multiplied by cosine theta, theta is t squared, at t equals 1.5. That's negative 8.072. And then when I go to find the derivative of y at 1.5, I'm going to do the same thing. In fact, I'm even just going to push second enter, which just copies down what you'd written before. The only thing I really want to change is that cosine needs to become a sine. All right, because y is r sine theta. Okay, so I come back in here. I click enter, and I get negative 1.673. And that's going to be all I've got for you for this video. I've got plenty of, released practice, and the keys for those are all available on the internet. In fact, I'll probably put all of these, the free response booklet, in the description of the video. So really with these, you need to practice them. You can watch me do these all day long, but I don't think that you'll get any better until you start working them yourself. So good luck out there.